So in my earlier video, I have just did that we are going to see one of the most interesting topic under the heading called as of your conductors, insulators and semiconductors. Of course, in your lower classes, we have seen that conductors means, of course, you can be given with that of your metals. They are very good conductors of that of your electricity and that of your heat. Insulators, when you are coming, of course, you can just see with respect to the wood, of course, general example, they are not very good conductors. Please mention that dry wood, they are not very good conductors of that of your electricity. And the semiconductors, of course, which is a branch which is lying in between these conductors and insulators. Now we are going to somewhat deal a high-fi knowledge of these three important class of the substance. That how you are going to classify a substance as a conductors, insulators and semiconductors. So before going to the depth of this knowledge, first I want to make you understand with respect to two important terms called as that of your valence band and the conduction band. So why I am making you aware of these two things is because with respect to these two things, we are going to classify our substances as conductors, insulators and semiconductors. So what do you mean by this valence band? So you have to just remember that valence band is like a band, okay, a strip of band which consists of that of your valence electrons of your substance, okay. Whereas conduction band means which is lying over that of your valence band. For example, if this is your valence band, on top of it lies that of your conduction band. And why we are dealing with this? Because whenever you are applying certain energies on certain substances, this valence band electrons try to jump to that of your conduction band electrons. And whenever they go to the conduction band electrons, these electrons will be the source for your conductivity. Will be the source for your conductivity. So that is, these electrons are the main culprits for that of your conducting of your electricity or that of your heat energy. That is only possible when the electrons from the valence band are jumping to that of your conduction band. Now you can ask me, sir, okay, now we have been said what is valence band and what is conduction band. How we are going to classify these substances as conductors, semiconductors and insulators with respect to these two bands? It is mainly because becomes whatever the difference of the gap is there with respect to this valence band and conduction band, we are going to deal here or classify the substances as conductors, insulators and semiconductors. Instead of choosing as a conductors, let me choose conductors as that of your metals, because metals are also called as that of your conductors. Of course, whenever we are dealing with the metals, of course in our lower classes we have been explained that okay, metals are the good conductors of electricity. But how? So when you're seeing, for example, if this is your valence band, okay, when in the metals we are observing the conduction band will be overlapping with that of your valence band. And that is the reason on generally small amount of energy if you are going to supply to these metals, whatever the electrons will be present in the valence band will easily jump to conduction band. And once they jump to conduction band, the conductivity will be carried out. More the number of the electrons in the conduction band, of course the conductivity goes on increases. That is the reason metals are said to be as that of your good conductors of that of your electricity and heat. Coming with respect to the insulators, what can be your sense? How will you explain it that they are bad conductors? Of course, the gap between that of your conduction band and the valence band will be very much high. So this gap is also called as that of your forbidden zone. Of course, you know the meaning of forbidden. We cannot enter. That is the reason whenever you are applying the energy, what happens? These valence band electrons can't easily jump. This is not possible. And that is the reason, since there is no electrons in the conduction band, conductivity doesn't take place. And that is the reason we are saying that insulators are the bad conductors of electricity and that of your heat. But the most important class now we are going to see is with respect to that of your semiconductors. So here what happens, if this I consider as a valence band, this will be your conduction band. So what we are observing, of course they are having certain energy gap, but that energy gap is very much less, nearly equals to 0.5 electron volt until now. That much very low energy gap is there. Of course, there is a possibility that whatever the electrons which is present in the valence band can jump to the conduction band by the application of energy. But what happens in a normal pure semiconductor, please mark my words, I am using the term as pure semiconductor, the conductivity is less. The conductivity is less. Though it is having the conductivity, but its conductivity is less than that of the metals. So by this way, we are going to classify the metals, that is your conductors, insulators and semiconductors, with respect to that of your band theory. This is called as with respect to the classification of the substances with respect to band theory, that is with respect to conduction band and the valence band. So in conductors or the metals, the conduction band and the valence band overlap with each other. And that is the reason the electrons can easily jump to the conduction band, resulting into its high conductivity. Coming with respect to insulators, this says that there is a large energy gap which is called as that of your forbidden zone, and that is the reason electrons cannot jump easily with respect to that of your valence band to conduction band, decreasing its conductivity. Coming with respect to the semiconductors, of course there is an energy gap, but it is very much less, in the order of 0.5 electron volt, and that is the reason electrons can jump. But whatever the conductivity observed in the pure semiconductors, that is less. So by this way we classify the substances as conductors, semiconductors and insulators with respect to the band theory. But the most interesting thing now we are going to deal is with respect to semiconductors, which is also called as that of your intrinsic semiconductors. As I mentioned that here conductivity is less. So now with respect to the chemistry, we are going to see that how to increase this conductivity of your semiconductors. As I mentioned, so whatever the pure semiconductor we are taking, its conductivity is less. So in order to increase the conductivity, what I have to make it? I have to make it impure. That is, I have to add some impurity to our semiconductors. So addition of the impurity to the semiconductors is said to be as a process called as that of your doping. So addition of an impurities to the semiconductors in order to increase the conductivity, the process is called as that of your doping. And whatever the impurities you are going to add, that is called as that of your dopant. Very much important these two terms are. Of course, you are going to also see in your physics with respect to second PUC itself. In the chapter called as that of your semiconductors itself, I hope so it will be coming. There also will be using the terms as doping and a dopant. So doping means what? Once again I am saying it's a process. It's a process of the addition of an impurity to the semiconductors in order to increase the conductivity. So that process is called as that of your doping. Whereas dopant means what? Whatever the impurity you are going to add, that is called as that of your dopant. So now with respect to the added impurity, we are going to classify your semiconductors as that of your N-type semiconductor and a P-type semiconductor. Very much important once again, because they can ask you their classification. Classify N-type and a P-type semiconductor. Now let us deal with it. What does it want to say? What do you mean by N-type and what do you mean by P-type? So first and the foremost thing, I have to make you aware that whenever we are choosing a semiconductors, of course it will be your group 14 elements, if you are remembering. That is, it may be your germanium, it may be your that of your silicon, anyone. That is group 14 elements. So group 14 means what? They are having the valence electrons. How much? 4. So now the added impurity also depends upon their valence electrons. So whatever the dopants we are adding, what we mean by dopants, the impurity, they're actually your group 13. If you're remembering, that is your boron family. That is having 3 valence electrons. I'm writing it because when you're seeing the diagram, you're coming to know, because our valence electron itself is playing a vital role with respect to the dopants. Coming with respect to group 14, what is there? Your phosphorus or that of your arsenic, which is having 4 electrons. Group 13, sorry, not group 13 and group 15. Phosphorus or arsenic, which is having 5 valence electrons. Yes. So depending upon what type of an impurity you are adding, it will be said as that of your N-type and a P-type semiconductor. Now let us deal with the diagrams for better understanding. So first of all, let us mainly go with that of your perfect crystal or a perfect semiconductor, which is the purest form. Of course, whatever the atoms you are seeing over here, they are that of your germanium or silicon, that is belonging to group 14, which are having 4 valence electrons. You can just see 1, 2, 3, 4. That is, they are having 1, 2, 3, 4. Each electron you have to just consider another, whatever the 2 you are seeing is from another atom. So they are forming a covalent bond type. So 1, 2, 3, 4. If I just write it, they are in this way: 1, 2, 3, 4. Another electron, whatever you are seeing, it is from the another atom. That's it. So each germanium or that of your silicon is having 4 valence electrons. As I mentioned, the added impurity is a group 13 element, for example that of your boron family. So what happens over there? Basically, we could just observe that it is having just 3 valence electrons. You can just notice over here. 1, 2 and 3. So this electron is from your germanium atom itself. So what is happening? There has been left a vacancy. There has been left a vacancy with respect to that of your boron atom. So what happened in turns over here? A space will be left vacant. So now we can say okay sir, now the vacant left the space has been left empty. What happens? Of course, there your plays a vital role. What it will try to do, we know that conductivity is mainly because of the flow of the electrons. So but here it has been created a positive center, which is called as that of your positive hole. So what it will try to do is, on conductivity, if you are applying certain energy, the electrons in turn, these electrons will try to occupy the position of this vacant site. So in turn what happens here, now the vacant site will be observed, that is called as a positive hole. In order to occupy it, another electron will jump. So like that, electron will try to occupy this vacant sites. So what we are observing, that there will be a movement of the holes. Even the electrons are moving, but on top of that, what you are saying, the holes will be moving. So whenever a charged particles are moving, what it will try to do, conductivity increases. Thereby the addition of your group 13 elements increases the electrical conductivity within a semiconductor. Let me say you once again what I want to say in a detailed way. So this is your boron atom. Okay. So here it is having just 3 valence electrons. Let me consider this one is your germanium, which is having 4 valence electrons. Okay. Here also you are having the germanium. Here also you are having the germanium. Here also you are having the germanium. Of course, utilizing this boron, utilizing its 3 valence electron, it has been formed a bond. You can just see over here. Okay, no problem. But here what happened? Here there is a vacant site. I am calling this vacant site as a positive hole. I am giving it as a charge of positive. So now what happens is, when you are applying certain energy, so this is a semiconductor which has been added with a group 13 impurity as a dopant, which is having 1 vacant site. So we know that conductivity, whatever we are observing, is mainly because of that of your flow of the charged particles. It may be your positive charge, or that may be that of your negative charge, no matter. So how here the charge moves is, this electron will try to occupy this position. Yes. So in turn what happens here, now the vacant site will be created. Now this electron will try to move over here. So now here what happens, vacant site comes. This electron will try to move over here. So here the vacant site is opened. Even though the electrons are moving, but what we are observing that holes are moving. Able to understand? So here was the hole, here now it came. Here was the hole, here it came. Here is the hole, here. So the conductivity, whatever we are seeing in a group 13 as a dopant, is mainly because of your holes, that is your positive charge holes. By this way, the impurity added increases the conductivity of that of your semiconductors. So this type of a semiconductor is called as that of your p-type semiconductor. So what is my p means here? Positive, that is holes. So these semiconductors whose conductivity is increasing with respect to the movement of these holes is called as that of your p-type. So how you are getting this p-type semiconductor? By the addition of your group 13 elements as that of your dopant or that of your impurity. Coming with respect to that of your n-type semiconductor, as I have mentioned, if I am using an arsenic, a group 15 element, of course it will be having how many valence electrons? 5 valence electrons. So in turn what happens here is your germanium, which is having 4 valence electrons. Here we can easily explain it. So here what happens, of course here they are forming the bonds, no matter with it. Germanium, arsenic, by utilizing its 4 valence electron, it is forming a bond. But we can observe that there is an extra electron over here. And whenever some certain energy is applied, what happens? These electrons will move. And whenever these electrons moves, what happens? Of course, conductivity will be observed. And this conductivity in these semiconductor is mainly because of this extra electron. If you can just see over here, in an arsenic, though it is having all the bonds, but there is one extra electron observed, which is called as that of your mobile electron. And this electron is mainly responsible for the conductivity, which is increasing the conductivity in terms of that of your semiconductor. And that type of an semiconductor is called as that of your n-type. Why it is called as an n-type? Because negative type. Negative means it is mainly the charge, and that is with respect to that of your extra electron. And when this n-type semiconductor is obtained, when you are adding a dopant as a group 15 element, which is having one extra electron. When your p-type is obtained, when you are adding an impurity called as that of your group 13, forming as a hole over here, a positive charge. So this classification is called as that of your n-type semiconductor and p-type semiconductor. So by the addition of the impurities, we are observing that how the conductivity is increasing. So in p-type, the conductivity is mainly because of that of your positive hole, the vacant site which is observed. Whereas in an n-type semiconductor, the conductivity is mainly increased with respect to that of your mobile electron. So by this way, by addition of certain impurities, we are going to increase the conductivity of your semiconductors, which has been classified as that of your n-type semiconductor and a p-type semiconductor.